Hey guys, so this section is polynomial and rational inequalities. It's called 3x because it's not actually in the textbook, but it is a technique that you'll use at the end of first quarter calculus for some derivative tests, so I want to make sure that you've seen it. So we're going to look at three methods in this section for doing the same thing. There's graphing test points and sine charts. Which method we use depends both on personal preference and then what the problem is that you're working on, whether or not it's polynomial or rational. For instance, the graphing method I really like for polynomials. I think it's easy, but I'm a pretty visual person. I hate plugging numbers into equations and just sort of the grinding out plug and chug stuff. That's test points, and for some people that's not bothersome, so I'll show that method, but it's not my preference. Sine charts are confusing, but I think they're the easiest way to do the rationals. Again, that's to me, but you can use any of these for any of the problems. You're going to get kind of my slant on it, but you can also decide that you prefer one of the other methods from what I'm using. So there's a bunch of steps here that sort of everything has in common, and I don't think they'll make a whole lot of sense unless I'm kind of presenting them with the problem. So I'll just go ahead and launch into the examples and kind of explain this part as I go. So I'm going to do this the same problem 3 times, and that's so you can kind of see each of the methods on the same thing. So this first method is going to be graphing, and kind of step 1 is to just graph what we have. So I'm thinking of it more as y equals, at the moment, x plus 3, x minus 3. And so that's going to get kind of just our graph going, and then we'll figure out the greater than less than part afterwards. So this is going to be x equals 0, x equals negative 3, and x equals 3 for our intercepts. And then this is going to, everything's crossing because these are all to the first. So this is kind of going back to what we saw in section 3.4. It's also 1, 2, 3 x's, so it's an x cubed. And so we would expect our graph to come in from the bottom and leave out the top. That was that end behavior theorem that we saw back in 3.3 and 3.4. So graphing this, I have a 0 here, here, and here. And then, again, we don't care how high or how low the top and the bottom of the graphs go, the mins and the maxes. We're just looking for a general shape. So if we're talking about something greater than 0, what that's really saying, and remember what would be out here is the y's. So we're saying the y's are greater than or equal to 0. So that would happen when the graph is above the axis, because that's where all the positive y values are. If we needed to find the less than 0, then that would be the regions below the graph, below the x-axis, because down here is where all the y values are negative. So if we look, we got positives here and here. So these are the 2 intervals where the graph is positive. If I cared, then these would be the 2 intervals where the graph was negative, but we do want greater than 0, so for this one we want the positives. And so then just looking at those intervals, that means my solution set is going to be, and I have equals on there, so that means I want to include my endpoints. So my solution set is going to be from negative 3 to 0, inclusive, union, and it picks back up at 3 where it's above the axis. And so that's going to go from 3, and then that goes forever, so on up to infinity. And so again, what we're looking for is what values I plug in for x here that are going to make the output, the y, greater than 0. So if I plug anything in this region, I get outputs greater than 0. If I plug anything in this region, I get outputs greater than 0. So that's the graphing method. To me, graphing polynomials is pretty easy. And you just get this nice visual, and it's just, above or below the graph is going to give you your solution sets. Okay, same problem, but this time it's test points. And so here we want to find the zeros of f of x, and we're going to use a solid dot on the graph because these are equals. So we know we want to, anything that equals 0 is okay. So we'd have a 0 at 0, we'd have a 0 at 3, we'd have a 0 at negative 3. And then what we do is that gives us 1, 2, 3, 4 intervals. So we grab a value from each interval. So negative 4 for this one. I used negative 1 here. I used 1 here. I used 4 there. And then we just plug them in here and see if they come out positive or negative. So if I do that, so I'm going to evaluate this at f of negative 4. So negative 4 plus 3, and negative 4 minus 3. And if I grind all that out, I'm going to get negative 28. And I won't bother to show the math. You could check that if you like. And so on this region, my outputs are negative. And that's going to carry all the way through to 3, because otherwise I'd have to have another 0. If I do the same thing with negative 1, just writing all those in so you can kind of see the math that I did do, that's going to come out to positive 8. So we're going to be positive in this region. Plugging in a 1, and then again, just grinding this out. So all I'm doing with that is 1 times 4 times negative 2, and cleaning that up and getting negative 8. So we're negative in this region. And then finally with the 4, plug all that in, and you'll get 28. And so this is positive. So since we want the greater than or equal to zeros, we want the positive regions again. And so that's going to be between here and here, and there to infinity. And so you can see I'm getting the exact same answers I got from the graph. I just had to do kind of a bunch of arithmetic to get there. And if you like arithmetic and you hate graphing, this might be a good method for you. I'm kind of the opposite. I like graphing, not so much on the arithmetic. So for me, if it's polynomial, I really prefer the graphing method. So our last method is sine charts. And these are confusing for a bit, and once you get how to do them, they're really easy, but it's one of those things that it takes a little bit to kind of figure out the process. So let's see what I can do with this. We're still solving the same problem. So the way that we set this up, and I have one set up in the notes to try to help students get it organized the first time. So we draw this chart. We list the factors, the x plus 3, x minus 3, on the vertical, and then the zeros that go with it on the horizontal. And so when I do this in class or when I do it on paper, I always kind of draw lines, and I do little dash lines here just to kind of help separate the intervals. It's just to keep it tidy. So here we have negative 3 is a 0 for this one, 0 is 0 for x, and then 3 is the 0 for this one. So if I am to the left of the 0, and there's no negative on the x, it's going to be negative values out here. And it's almost harder to see with the x. If I start with the negative 3, you can see if I put in negative 4 into this, something from this interval, it comes up negative. So this is kind of like doing the test point method, but without actually doing any math. We're just saying, yeah, negative 4 in here would be negative 4 plus 3, that's a negative. Over here, you know, negative 2, negative 1, that would keep this positive. And then once it's gone positive, once you get past that 0, it's not going to change signs because it's linear, so it's only going to have 1 0 and 1 sign change. So going back up to the x, so if it's negative 4, it's, you know, kind of obviously negative. Anything past 0 is going to be negative. And then these regions are going to be positive. Likewise here, if I put in negative 4, it's negative. If I put in negative 1, it's negative. If I put in 1, it's still negative. There's 0, and then if I get up past the 0, then I have a positive, like if I plugged in a 4 to this. And so really, if you kind of accept that as long as there isn't a negative on this x, it's going to go negative, 0, positive, negative, 0, positive, negative, 0, positive, pretty much every time, other than in the event of a negative. And if there's a negative, that just means it's going to be backwards. So then what we do is we go, well, we got 3 things multiplying, right? So if I multiply 3 negatives together, it's a negative. If I multiply 2 negatives and a positive, it's positive. 1 negative, negative, and all positives makes positive. And once again, we want positive or equal 0. So that's going to be, there's my zeros. And the positive regions are right here and right here. And that's the exact same answer as I got the last 2 times, which is good. Negative 3 to 0, and then union that with 3 to infinity. So, like I said, I hate test points, but that's just me. I like a sign chart because there's not a lot of calculation. I'm just kind of following the signs. I like these ones for the rationals, and then for polynomials, I like the graphing method. So that's what I'm going to show. But you can use any of the three methods on any of the problems. Graphing on the rationals is probably not recommended because the rationals are those ones you just graphed in 3-7 that took like 7 steps and was really involved. And so for the rationals, I would not pick the graphing. I would pick either sign charts or test points, whichever seems more comfortable. Okay, so here we have another polynomial one. And so I'm going to do this by graphing because, like I said, that's my preference. So that's how I'll show it. Right here I got x equals 0, x equals -2, and x equals -5. This is squared, so it's going to bounce. These are both to the first, and so they are going to cross. And if I do kind of just a quick sketch graph, it doesn't even have to be a good graph. 1, 2, 3, 4, 5. I have a 0 here, I have one at -2, and I have one at -5. For my function, I have 2, 3, 4 x's, no negatives on the x's. That means this is x to the fourth. So it's positive even, and it's going to kind of look like x squared. So we'll start up here at the top, and then we're going to cross through the -5, and then we're going to cross through the -2, and then we're going to come back and bounce off of the 0. And so our graph is going to look something like that. And this time we are looking for the negative regions and the zeros. And so, because we want less than 0, so that means we want below the x. I want numbers that if I put in for x, I get something negative out. So that's going to be here, and the sneaky point right there. So at x equals 0, this thing comes down and touches 0 and then bounces back up. So we do have to include that point also in our solution set. So our solution is going to be -5 to 2, and then union that. When we have a single point like that, for interval notation, we use those braces, trying to make decent ones, and that indicates just a single value. So for this one, another polynomial, so I'm going to do graphing. We got 2, 3, 4, 5 x's, so x to the fifth is going to look like x cubed. And we got x equals 0, and that is going to be a bounce. We got x equals -3, that's going to be a cross. And x equals -5, and that one's going to be a bounce. So I will draw a little graph here. 1, 2, 3, 4, 5. So our zeros are at -5, -3, and 0. And so we're going to start at the bottom. We're going to come in. We are going to bounce off a -5. And then we're going to come up and we're going to cross on the 3. And then we'll come back and we'll bounce off of the 0. And so this time we want the negative regions and the zeros. So that means we want, we want the greater than, my bad. We want the positive regions and the zeros. So we want right here, and right there, because that one is also a 0. So we go -5, and then we're going to union that from -3. So right here, if this had no equals on it, I'd have to say from -3 to 0, and then from 0 to infinity. I'd have to split it with parentheses. But since it has an equals, this is just one continuous region. So I can just write that from -3 to infinity. Okay, so then we move on to the rational ones. And like I said, for these, I prefer sign charts, but if you prefer test points, that's cool, do test points. I'm going to factor this first so I can kind of see what I got going on. So we got x plus 3, x plus 2, and x minus 2, greater than or equal to 0. So we'll be looking for positive regions and zeros. We list our factors vertically. And then we draw our number line down here. And so I have zeros at -3, -2, and 2. Don't worry about getting the scale right on this. Make it like kind of nice and big so you can see what you got going on. I'll see people try to like cram, the numbers all close together and try to draw this, scaled, and then it just makes it hard to read. So don't worry about the scale. So -3, that one's 0 is right here. And then now that we have a denominator, we need to be a little bit careful to not include these zeros because those are undefined, right? Those would be not in the domain of this function. So what I do is I write a little u there to just kind of remind myself it's undefined. And that's kind of my way of saying don't include that in your answer. And then we end up with, so we have 1, 2, 3, 4 regions and 3 things to check. So, again, if I tried -4 in here, it would come up negative. If I tried negative, 2.5 in there, it comes up positive. So there's that -0 positive again. Same thing's going to happen here. So once you can kind of figure out that it's going to go negative and then to the 0 and the positive, it's great. The 2 things that can mess it up, like I said, are if you had like a -x plus 2, that one is going to be positive on the right and negative on the left. If you try a couple of points in there and check. And then also if we had something like a squared, you can either write it twice so that you catch the square, or you just have to realize that something squared is always positive, or at worst case 0. Because no matter what I put in here, remember this graph looks like it'd be coming and bouncing off of -2. And so this is always positive. So those are kind of the 2 things you can run into that are a little bit funky. But otherwise it's going to go -0 positive. And then we just tally these up and compare it to what we need. So I got 3 negatives is going to be negative, 2 negatives will be positive, 1 negative negative, and 3 positives for positive. And we want greater than or equal to 0, so I want the 0. I do not want the undefined, so I got to think open dot there. You don't have to draw the graph, I just find it helpful for translating it to the interval notation. We don't want the endpoint because it's undefined, and then this is going to go out to infinity. So our solution set is -3 to -2, union 2 to infinity. Okay, so this one, if I factor that numerator, it's going to be x minus 6 quantity squared. I could also write it x minus 6, x minus 6, and then set up the 2 separate factors. That's going to be over x plus 5 and x plus 8 less than 0. So this time we want the negative regions and we don't want any of the endpoints. So that makes it easy. We don't have to pay a whole lot of attention then. So x minus 6 squared, x plus 5, x plus 8. We'll do our number line. And so I have zeros at -8, -5, and +6. So 0 there, 0 there. Actually, I guess I should write undefined, although it doesn't matter because there's no equals. So again, if we have 3 things, we have 4 regions. And I'll just kind of do this and that. And then, so here's where we don't negative, negative, negative. This one is squared, so this is always positive. And then the only thing that's going to contribute is a 0 right here, which in this problem isn't actually going to matter because we don't need the equal 0, but it can. These ones are just regular, so negative, negatives, positive, positive, negative. There's our 0, and positives the rest of the way. So down here I have 2 negatives, so that's going to be a positive. I have 1 negative, so that's going to be negative, all positive, and all positive. So we want the less than or equal to zeros, or sorry, just the less than zeros. So the only place that happens is right in there. So our solution set is going to be -8 to -5. And this last one, it's not equal or greater than less than 0. So that means we have to do a little bit of algebra to get this in the right form. So this is going to come out, let's see, we're going to do 2x minus 1, 4 minus x. I'm going to add this 2 over, And then I'm going to need to get these combined. So I'm going to get a common denominator going here. So 4 minus x, 4 minus x. And I'm doing this because I need something factored. So I need it to all be multiplying or dividing so that I can use the zero property. And that's going to be less than or equal to 0 now. Now at the over common denominator, I can write that together. And then my numerator is going to go 2x minus 1. 2 times 4 makes 8. 2 times negative x. Less than or equal to 0. So 2x minus 2x, those cancel out. Negative 1 plus 8, that's 7 over 4 minus x. And this is less than or equal to 0. So this thing only has one 0. And it's at 4. So if I put in something less than 4, 4 minus, say, 3, 4 minus 3 is positive. And so this side would be our positive. If I put something bigger than that, say 5, 4 minus 5 would be negative 1, that side's negative. And that's what I was saying is when we have a negative x, it does the opposite. It goes positive, 0, negative. And we want the less than 0, so our solution set will be from 4. And, oh, that's an undefined. So I can't include that point because it came from the denominator. I forgot to say that. Up to infinity. And that wraps up chapter 3.